Thank you for the introduction. So I'm going to present you PERK, which is a joint work with all the people mentioned here on the slide. So what is PERK? PERK is a signature scheme based, as the name suggests, on the permitted kernel problem. How it is built, it is another Fiat-Shamir-based signature. So it comes with proof of knowledge. And this proof of knowledge is built using MPC in the end. And in the specific case of PERK, we are relying on a variant of the PKP problem that we have named relaxed inhomogeneous permitted kernel problem, or RIPKP. So what we are going to see is the following points. So we will start to explain how you build a signature from a proof of knowledge, and then how you can create a proof of knowledge from MPC. So I guess it's already the second time you will hear about this during the workshop, so I will try to be a bit fast on those two parts. And then we will move to what makes actually the core of PERK, namely our proof of knowledge for RIPKP. And then we will discuss the resulting signature we get in terms of sizes, performances, advantages, and limitation. So let's go with the first item. How do you build signature from a proof of knowledge? So quite informally, a proof of knowledge is an interactive protocol between a prover and a verifier. And you want several properties for this proof. First one being the correctness, the fact that an honest prover should always be able to convince a verifier that he knows some secret. And you also have the soundness, which ensures that a malicious prover cannot convince a verifier that he knows the secret, except with negligible probability. And we also want zero knowledge, in our case, honest verifier zero knowledge, which ensures that nothing is leaked about the secret. On why those proof of knowledge are important for digital signature, it's due to the work of Fiat and Shamir that allow to transform a public coin interactive proof of knowledge into a digital signature. And the main idea to do this is if the verifier only returns strings that are sampled uniformly at random, then you can replace it by a hash function that you model as a random oracle. And that's it. And the security of the Fiat-Shamir transform have been well studied over the age. It was first proven secure for 3-round protocols. It was later extended to n-round protocols. And its security in the quantum random oracle model has also been quite studied. So now we have reduced our problem for designing a signature to just designing a proof of knowledge. So let's see how we can do this from MPC. So this has already been presented extensively yesterday by Thibault. So let's say you have some secret X and you can recompute it from several shares for the secret. An MPC protocol will allow a set of parties which have each as input one of the share of the secret to compute y is equal to f of x for some function f without leaking anything on the secret. So you have two important properties in our case, correctness and privacy. And in the context that is interesting for us, namely designing Fiat-Shamir-based signature, we will model the adversaries as honest but curious. So once we have MPC, we will turn this into proof of knowledge using MPC in the head. So same idea as yesterday. The main goal, the main idea is for the prover to generate all the shares. He will commit to them, and then he will emulate in its head the protocol. And in the end, he will reveal the views of n-1 parties. On doing so, the verifier will just have to check the commitment to the share, check the computation of the MPC protocol, as well as its result. And that's basically what we need. Few important comments to mention. When you do this, what do you obtain in terms of proof? So the resulting proof of knowledge have all the properties that we are interested in, namely correctness, which directly stems from the correctness of the MPC protocol. It also has zero knowledge, which comes directly from the n-1 privacy of the MPC protocol. And soonness error equal to 1 over n. And if this quantity is too small, which is the case for almost all the time, then you can make it negligible by repeating the protocol as many times as needed. As it was explained extensively yesterday, if you do this, you obtain a proof of knowledge whose size is quite big. So on top of this, you want to apply several optimization, such as compressing all the commitment together by hashing them and using Merkle tree for the seeds. And if you do this, you are able to reduce significantly the proof size, hence also the resulting signature size. Okay, so let's now jump to what really makes the core of PERK, namely our proof of knowledge for the R IPKP problem. So let's start by discussing the actual underlying problems we are using. So we are using the PKP problem here, which was initially introduced by Shamir. And we can state it as the following. So let's say we have an M times N matrix H over FQ, and we have some pairs of vectors xi, yi. And along with this, we take permutation, and we want the following property to hold, namely the product from the matrix H to pi of xi is equal to yi, and this has to hold for all the t pairs of vectors we are considering. And the PKP problem asks an adversary to find a matching permutation for this. And it was not stated like this initially by Shamir, especially the first definition that was proposed only consider t is equal to 1, which is now referred as monodimensional PKP in the literature. But over the year, people also took interest in the case where t might be greater than 1, which we will refer here as multidimensional PKP. So this is, let's call it basic problem. And let's see what we are using as a variant. So what we have called the relaxed PKP problem is the following. So all the inputs are exactly the same as in the PKP problem, but what you are asking to the adversary is a bit different here. Here you are asking to find a matching permutation for a linear combination of the xi. So you can see it as solving the PKP problem monodimensional 1 for t is equal to 1, but with an extra degree of freedom, namely you can solve it to any linear combination of your choice from the xi's. So this is the problem we are going to use. So let's see what is known about its security in the literature. So the monodimensional case have been well studied, starting more than 30 years ago by the work of Georgiades. And it has been improved over the years. And to date, the best known attack is the one from SBC22, which is due to Santini, Baldi, and Chiaraluce. Hopefully I'm not destroying the names here. And what is nice also in this paper, it is that it has also generalized all the existing attack in the monodimensional case to the multidimensional case. What will be of interest for us, of course, is what are the attacks on RIPKP. So they are fairly new as we have introduced the problem, but what you can find in PERK if you check the specification is that we took the best known attacks and we have generalized them to the case of RIPKP. And something that is worth mentioning is that in order to be conservative in terms of parameter choice, we restrict ourselves to very small values of t's. So we only consider t is equal to 3 or t is equal to 5 for the scheme. Okay, so now that we know a bit more about the problem, let's see how the proof works. So PERK inherently is a 5-round proof of knowledge. And we have two main points that are important to understand. The first one is, why are we using the RI-PKP problem and not, let's say, the initial PKP problem? We do this in order to implement the challenge space amplification technique that allows us to have a big first challenge space size, in our case q to the t minus 1. And why do we want to do this? Because this has a direct implication on mitigating the Carl-Zanzavorecha attack on 5-round proof of knowledge. So this motivates the use of the RI-PKP rather than, let's say, the full PKP. And the second ingredient that is important for PERK is the use of the shared permutation technique. And this technique allows to compute the permutation of some vector x without learning anything on pi. And this follows the MPC in the head paradigm. So you have some shares, a permutation on the random vector that plays the role of a mask. And the main point is that you want to decompose your permutation in the composition of all the pi. And you also have this value v computed like this. And with all of this, what you can do is that now you can compute pi of x plus v by recurrence starting from S0, x in your case, and in this case, on taking Si being equal to pi I of Si minus 1 plus Vi. So this is the two main points in the proof. If we want to have an idea of how it works, here is a very high-level description of the protocol. So the prover will start by sampling all the shares with the additional constraint that you want P1 to be of a specific form, because here you want to use the secret. You compute V, and then you compute both, you commit both to the shares and to H times V. After this, you get the first challenge, which is basically the linear combination you will try to solve the problem for. And then you have the core of the MPC protocol, which in our case is using the shared permutation technique on the vector S0, which is a linear combination of the xi. And once you do this, it's full classical MPC in the end. After this, you get challenged on a given party. So you will reveal the views of all the party except the one you have been challenged to. You will, in addition, get some value, in our case S alpha, in order to be able to recompute the protocol and check the result. And if you do this as a verifier, you just have to check basically all the commitments, the one on the shares, the one checking the MPC protocol execution. And finally, you want to check the value HV using the equation H times Sn minus the linear combination of the Yi. So this is pretty much how PERK work. So let's see. So this is the high-level description. On top of this, you want to add all the optimization we have mentioned previously and that were described in detail yesterday. And if you do this, you will get the following sizes and performances. So let's first have a look on the sizes. So like in most MPC protocol, public key and secret key will be rather short because pretty much everything that is costly comes from a seed. And regarding the signature, we will have some term that is multiplied by the number of repetition we are doing, this number being tau. And in our case, what we have to send is a vector as well as a permutation on the usual part of the MPC, so the seed for the tree and the commitment for the remaining parties. And if you do all of this, you end up with the following sizes. So as it was mentioned yesterday, most of the MPC protocol have sizes between 5 to 10 kilobytes. So for PERK, we are kind of on the low end here with sizes that can be as short as 6 kilobytes. And we have the following performances. And as usual with MPC, you can have a trade-off between size and performances. So if you are willing to trade a bit of signature size, you can reduce the performances by a factor 5 or something like this. Okay, so let's see, and let's conclude with advantages and limitation of PERK. So most of them are pretty much I would say all the same of all the MPC protocols. So we are good on the public key plus signature size metric with, in addition, small keys. We use as an underlying harness assumption, we don't use any structure, no trapdoor here. And we are resilient against potential attacks on the underlying problem. This is due to the fact that a big part of the signature size is actually just related to the MPC part. So in case you need to increase the parameter, it has only a limited impact on the signature size. As limitation, we kind of share the same as all the MPC-based schemes. So this is relatively slow. Let's say if we compare to scheme like Lattice's one, like Dilithium, it also has relatively large signature sizes. And in our specific case, we rely on the variant of the PKP problem. So that being said, what do we have next for PERK? So here, a bit cautious disclaimer, everything here is work in progress, so results are not guaranteed to be as I mentioned. But what we expect in the following months is to be able to do an update which will reduce the signature size by approximately 5%. And we also plan to improve our implementation, especially currently for level 5 parameters, our implementation use lots of memory, so we will address this issue. And hopefully we can also have speed up on performances, we will see. If you want to know anything about PERK, there is a website, everything is here. Or feel free to ask me if you have any question.